We're going to be taking a look at this model of Tenkiller Dam. The model looks complex, but it's actually more tedious than it is complex. It was developed to estimate the change in habitat units that would result from the addition of a weir dam downstream of the spillway structure for Tenkiller Dam in Oklahoma. So this happens to be Oklahoma in the United States, and this dam here is called Tenkiller Dam. The water behind the dam is quite deep and quite cold. There is a spillway structure over here, and this is used to allow water to be released into the Illinois River, which runs downstream of the dam for many, many miles. The presenting problem was that the water in the Illinois River downstream of the dam was very low in dissolved oxygen, and it was quite warm. The river had trouble sustaining trout populations, and this is the trout capital for Oklahoma fishing. The lake is deep, and water at the bottom of the lake was very cold, but it was lacking in dissolved oxygen. So an early proposal was to release the water, detain it briefly with a weir dam, and this dam would be punched full of holes that would help oxygenate the water. The effects of this proposal would be experienced over several miles of water. To evaluate the effectiveness of the measure before it was implemented, we used the U.S. Fish and Wildlife Service habitat evaluation procedure. That procedure is described here at this website. The basic idea behind the HEP, or Habitat Evaluation Procedure, is to identify a number of representative aquatic or terrestrial species and then measure the affected area and multiply it by a sustainability index to get a number of habitat units. So this equation here basically describes this process. You identify an affected area. For this example, this made-up example, I've said, suppose we have 100 acres. And we are looking at a specific species. It might be largemouth bass or catfish or trout, but it's only one species. And we say for this species, the suitability index, a number between 0 and 1, where 1 is a perfect. I still haven't figured out how to solve that problem, and I apologize. Where 1 is a perfect habitat and 0 is a perfectly awful habitat. You then multiply the suitability index by the area and you get habitat units. So a 0.67 here suggests that this is reasonably habitable. A 0.75 would be an area that's even better suited to this species. So let's return to our model. Here we have the habitat evaluation procedure, and they have developed a number of habitat suitability index models. So to get that suitability index that we were just talking about, you would use one of these habitat suitability index models, and they have been prepared for a great number of species. This has been done by the United States Geologic Survey. We're going to look at the model for largemouth bass. I'll return to this page in a second. I had selected it earlier. I would like you to see that these models in particular were developed back in 1982. This is a model that is strictly for the largemouth bass. And if you were to take your time scrolling through here, which we will not do, what you would find is that there is a life history. There's been a great deal of science that's been gathered and collated here. But our interest is really in just understanding our basic model here. So let's go to this page. A suitability index is obtained from an HSI model. Notice here that the desired endpoint is shown on the right, an HSI, a Habitat Suitability Index. To get that index, we begin with a varying number of habitat variables, shown on the left, which are all aggregated to describe the quality of the species' required life requisites. So over here we have habitat variables, and on the right we have the HSI, and down this side we have the life requisites. So the largemouth bass requires food, cover, water quality, reproduction conditions, and some other life requisites. These are all described in this 43-page model. The task then is to go out and to identify values for each of these habitat variables. So now let's look at our quantitative risk assessment model. We have 3 species: bass, catfish, and trout. We also have 4 sections of the river. Site 1 is closest to the dam. Site 4 is farthest. We also have 2 conditions. The without condition shows conditions as they existed at the time of this analysis, before the plan was implemented. The with condition shows how habitat variables would or would not change as a result of this weir dam being constructed. So take a look here at the very first variable. This is variable 1, the percent pool cover. It was determined that at site 1 there was about 73% pool cover. This would not be changed by the addition of a dam. I'm not going to go through all the variables. It would be terribly tedious to do so. But I would like you to have a basic idea of this model. So here we have habitat variables. If we scroll on down, you can see in here we've summarized the life requisites. These life requisite values are also indices, numbers between 0 and 1. So a 0.59 for food would say that on a scale of 0 being intolerable to 1 being perfect, this hits at about a 0.6. You would notice that with the dam or without the dam, the food requisite does not change. One of the life requisites that does change with this dam is water quality improves. So these life requisite values are used to calculate a habitat suitability index. So the suitability of this Site 1 stretch of the Illinois River for bass under existing conditions is very low. It's a 0.1, close to a 0. With the weir dam in place, it rises to a 0.39 for an improvement or a change of 0.29. We have here the habitat suitability, the area in acres, and an estimate of the number of habitat units. This number is calculated based on using all of this information above. And that sounds terribly complex. It's just a lot of arithmetic. So what we end up with then, in this particular example, we have 1.8 habitat units existing. If this weir dam was built, that would increase to 7.3. But there's a lot of natural variability, as you might expect, with these habitat variables. And there's a lot of uncertainty due to the lack of knowledge. So that if we use our Monte Carlo process, you can see that the values, we're not exactly sure what they are. The same thing's going on for catfish. Let me scroll on over here to the beginning of the catfish model. This has its own set of variables, its own set of life requisites, and we have its own set of habitat units for the catfish as well. The same thing is true for trout. Once again, we have a number of variables, and once again, we have a great deal of uncertainty here. For example, if we grab this one variable at random, the percent cover for adults, we can see that it's somewhere between 2 and 15%. Most likely it's about 8.5%. So if we were to scroll through and look at the different inputs here, you see variables all over the place. The colors are color coding because some of these variables occur in all three models, and we want to make sure that if they do, that they are using the same values. But once again, we have a number of habitat variables here. The life requisite calculations here, and the habitat unit changes that we are interested in. Once again, you see Site 1 is not very suitable. Not for trout, for catfish, or for bass. So we have a totals page here, and this is a page where we have just grabbed those cells and summed them. So you can see here, for example, we can summarize our results by the site. So in this particular iteration of the model, there are about 20 habitat units in Site 1, about 20 in Site 2. Site 3 has a sizable improvement, 43 habitat units, and in Site 4 it's down to 4. If we were so inclined, we could look at the results by species. There are more improvements for catfish, channel catfish, than there were for the rainbow trout or the largemouth bass. What we're interested in, however, just for our purposes, will be this change in habitat units. So we're going to run a simulation. I'm going to run a simulation of 5,000 iterations to demonstrate how all of that uncertainty, how all of those many, many variables and the different locations, how that uncertainty plays out. Let's close this. We're going to open a browse of results, and you can see here are our results then. We don't know exactly how many habitat units will result from the construction of this weir dam. It's somewhere between 32 and 114. Most likely it's going to be the 75 that you see here. We are 90% sure the improvement in habitat units will be between 56 and 94. And so those numbers would be used and compared to the cost to determine whether or not this project is worth constructing. As it turned out, this project never was constructed, and in fact there is a story here from Oklahoma's own Channel 6 that's talking about lowering the water temperature in Lake Tenkiller, and this was done to help the fish thrive. And the article describes how instead of a weir dam they used a pipe to add oxygen to the water as it was being released. So it's rare, perhaps, to see how risk assessment was used to actually make a decision. But in this case, this risk assessment showed that the improvements in habitat were not great enough to justify the size of the expenditure to build that weir dam downstream of the spillway structure that you're looking at here.